Okay, so our last talk of the day is David. He did his PhD at the Antiquaria University in Colombia, and he's now a postdoc here at IIP. He'll be talking about type 1+2 seesaw models in light of the new neutrino oscillation measurements. Thank you.
Thank you, Gabi. As I'm David Suarez. I'm gonna talk about an update on Taiwan Type 2 seesaw model in light of new measurements of neutrino oscillations parameters. So as all the previous talks, or most of them said, we need to provide an explanation for neutrino oscillation phenomena, and a way to achieve that is to propose an extension of the standard model, which can contain a mechanism to generate, for example, a Majorana mass terms for neutrinos. One of the possible models that generates this kind of terms is a 331 model, which, as Patricio said, promotes the SU2 left symmetry to use SU3L symmetry, which this symmetry can explain the number of families in the standard model, why they are three families via anomaly cancellation conditions and asymptotic free. And so in this model we consider the leptons where the leptons are triplets of SU3, and the third component of the triplet we will represent a new neutrino species, that will be heavy, as I will show later. And as expected, right-handed neutrinos remain as singlets. In order to give a mass term for a Majorana mass term for neutrinos, we introduce an scalar sextet that acquires BEV, and it breaks down into an SU2L triplet, and SU2L doublet, and a singlet. The most important of them would be the triplet that would feature lepton flavor violation signatures. So via the Yukawa Lagrangian, we can generate this Yukawa Lagrangian. We can generate a mass term for actin neutrinos, which here we have the Majorana, the 6 times 6 matrix in a time 1+2 seesaw mechanism, and after that, analyzing it, we obtain these values for the masses of the actin neutrinos and the heavy neutrinos. These BEVs of the scalar sextet, have important constraints. For example, the BS11 and BS13 have constraints for the contribution to the W and C bosons, and the lambda must be heavy now in order to about constraints about the search for W prime and C prime bosons, which are a characteristical feature of these kind of models. So, as I said, the scalar sextet breaks into a triplet, and this triplet is gonna contribute to lepton flavor violating processes, like which have some constraints. We have the relative immune decay, which is the one of decay of the immune that is shown in this Feynman diagram, and we have also the decay of immune into three electron, positron, electron decay. So we obtain that the branching ratio is given by this equation, and that allows us to connect the physics of neutrino oscillations with the physics of lepton flavor violation. When we consider we have two contributions due to the singlet scalar and the doublet scalar. When we consider a scenario when the singlet scalar is degenerated with the doubly charged scalar, we can connect, for example, lepton bounds of doublet scalar and with the lepton flavor violation phenomenology. As usual, the Yukawa couplings can be expressed in terms of neutrino oscillations observables, like the PMNS matrix and the masses, the neutrino masses. We consider here in our analysis. Second, we have this contribution to the decay into 3 leptons of the muon, we consider here these benchmark points. We consider here a normal hierarchy because, for example, Atacama results show a preference for a normal hierarchy as new results for 2K and NOAA. So we use these benchmark values for the neutrino oscillation parameters, and with them we compute the branching ratio and obtain the following graphs. We vary the values of the lightest neutrino Einstein and the as I forget to say, we consider a scenario when the main country where the type 2 seesaw is the most dominant one, because we consider that the relation between the lambda and the BS13 is small enough to render that result. So in the x-axis we have the branching ratio of mu to E gamma as a function of the mass of the doubly charged scalar, and we have also here plotted the bound for LHC on the mass of the doubly charged scalar and the make limit on the branching ratio of this observable. And this is the plot for the another processes, the decay of mu free leptons in terms of these for the value, these values of the lightest neutrino mass eigen on the wave of the wave of the scalar sextet. We also use another benchmark in order to compare results, and we see that a neutrino that the radiation ratio is really sensitive to small changes on the parameters of neutrino oscillations. So as we know, this kind of lepton flavor violating searches can provide a really great test for physics beyond the standard model. So we update the predictions, the bounds of lepton flavor violation processes in a model with 331 symmetry and Majorana neutrinos, including new values for the parameters of neutrino oscillations, and show the impact in the model phenomenology. So thank you.
Thank you, David. Any question? Something online? No.
Thank you for your presentation. So my question is, these right-handed neutrinos are expected to be like in a heavier scale of mass, right? So the contribution to the cosmological effective number of neutrinos is expected to be low. That's right, like suppressed.
Why? What do you mean contribution?
Do the effective number of neutrinos in the early universe, like the constraint derived from the CMB?
What is the new species, relativistic species here?
That's my point. There is no relativistic species because the Majorana are not relativistic, are heavier. That's it?
Yeah.
I see. Thank you.
Thank you. Any more questions? No, let's thank the vegan. I'd like to make just a few comments on our schedule. We needed to do a little change, and